Hey. I'm Jan, and I'm going to tell you about light path guided culling for hybrid real-time path tracing. So I actually have a cool acronym, and it's LIPAC, right? Light path guided culling. And so to achieve photorealistic images like the one you see on the right, we need a way to compute indirect lighting accurately. And that is pretty much impossible to achieve with just rasterization, right? Path tracing, on the other hand, can solve the rendering equation exactly and therefore produce these photorealistic results. So while path tracing is quite expensive, the GPU accelerated ray tracing and some denoising and sampling advancements from the last years make it more and more a possible option for real-time renderers. Okay, so let's have a look at how GPUs actually do this ray acceleration. And to do so, they need acceleration structures. We already heard about this, but just so we're all on the same page. We have bottom-level acceleration structures, which basically encapsulate a single mesh, and then top-level acceleration structures, which are meant to encapsulate the entire scene and reference the bottom-level acceleration structures. So when we jump from like the small research rendering scene you've seen throughout the last papers to like real big scenes when we want to render entire worlds or big cities, we can quickly run into significant bottlenecks. So first of all, the acceleration structures can grow quite large in graphics memory. So the TLS gets large when we have many instances, and the BLSs can also consume quite an amount of memory. We run into a big problem in scenes like this compared to rasterization, which is that when we rasterize the image, then we can use instant drawing, right? We have a single mesh and draw it multiple times. And while in theory, BLS sharing is possible as well, it is not possible anymore when vertices are transformed uniquely. So think of, for instance, running animations on models, or also models that are like statically but uniquely adapted to the environment. So for instance, in this NO-City scene, we have many buildings that are like uniquely transformed to fit the terrain they're placed upon. At this point, each instance needs its own bottom-level acceleration structure that can easily consume way too much memory for real time. Okay, furthermore, when we have a lot of running animations, so for instance, many units roaming the street, we can quickly run into problems with BLS rebuilding. We've seen this before in the presentation, that this can be quite a slow process. And even if you just refit all the BLSs, it can be a bottleneck as well when you have like hundreds or even thousands of running animations. And furthermore, when we have as many instances as we have here, which are like multiple 100,000 instances, the build time for the top-level acceleration structure can become a bottleneck as well, and we have to do that in every frame. All right, so what do we usually do in computer graphics when we need to render large scenes? We employ some form of culling, right? And we have some quite battle-proven algorithms like Frost and occlusion culling that we usually use for rasterization approaches. The thing is, they don't really work well with ray tracing. Think of, for instance, a large surface behind the camera that still throws significant light on the scene. Then we just we don't want to cull that, right? Because it still contributes to the lighting of the scene. Similarly, when we look into a mirror and we see lots of instances behind the camera, we also don't want to cull these instances. So what games have been doing for the last couple of years is they employ some culling heuristic based on the object size and the distance between object and camera. And this usually requires or is implemented with an iteration over all instances on the CPU where we check, are they important, are they not important, then include them or cull them. And this can be quite a bottleneck in real-time games because you might have many instances. Furthermore, and like more importantly, this heuristic cannot be really good because either we have to cull a lot of objects that are in the distance and like quite small on screen but might still contribute significantly to lighting, or we include many instances that are not important at all. And the fact is that in most cases, something like Frost culling is a good idea, right? Because when you're just viewing a scene, then usually the stuff behind the camera does not contribute to the lighting. But the thing is, we can't know, and in some instances, it is very important what is behind the camera. So ideally, we would like to have a culling strategy that culls all those instances that do not contribute to lighting of the scene. But that is very hard to predict. So what if we just count how many light paths are intersecting each object during ray tracing. And if we like freeze those counts and zoom out, we can see that most of these instances are not hit at all, and we can simply cull them from the acceleration structure. This idea is often called hit feedback, and it has been proposed before, but just for like some very specific purpose, namely the prioritization of BLAS rebuilds. We instead want to employ a general culling strategy on top of it. To do so, we associate a culling state with each instance in the scene, and the state is decided based on the number of light paths that this object encountered during tracing. And the state then decides in the future whether this instance should be culled from ray tracing or not. But we quickly see a problem with that, because when an object is culled, it is obviously not encountered by any rays anymore, right? So what we do instead is we don't just cull the object entirely, but we replace it with a bounding box. And this bounding box has only the purpose of counting the light paths intersecting that area of the scene. And I also told you that the number of instances can be a problem, and we haven't reduced this so far. So what we are also doing is we don't just replace one culled instance with a bounding box, but we like group them together spatially and place them in these cells you can see in the image here. All right, so on the GPU, we have basically 3 important steps in our pipeline for this culling algorithm. First, in each frame, we build the top-level acceleration structure. Then we use that to trace some rays. And at this point, it doesn't really matter if it's path tracing or just like some other more lightweight ray-traced real-time technique. And then in the end, after the ray tracing, we process this hit feedback. So what we're doing during ray tracing is each time an object gets hit, we actually increase the counter in an associated hit feedback buffer for that instance. So like each instance in the scene gets an entry in this buffer. When we encounter a hitbox, we also increase the counter for the hitbox, but we effectively ignore the hitbox by just continuing the ray on its path. And this means the hitboxes, like the spawning boxes you saw in the previous image, they do not contribute to the lighting that is computed. Then, afterwards, we iterate over all instances and hitboxes and re-evaluate their states. So if an instance was culled, for instance, but the associated hitbox gets many light paths, many light hits, then we want to activate that instance again, and the other way around as well. And only during the next frame then, during TLAS building, we evaluate whether an instance should be included into the TLAS or not based on the state we previously computed. Right, let's have a look at the city scene. And let's freeze and visualize the acceleration structure. And we were looking at the mirror all along. And as we desire to be, the instances visible in the mirror were not culled, while the instances occluded by the mirror gets culled correctly. All right, and this basically means, with all the steps I've shown you, that we have a fully GPU-driven acceleration structure management algorithm. While this is great and avoids like any CPU-side bottlenecks for ray tracing, we quickly run into the problem of latency. So what I've shown you already clearly implies that we have at least like 1 frame of latency, right? Because an object gets hit a lot, then only in the next frame is it actually included for ray tracing. But it gets even worse, because when an instance is activated, we might first have to build the bottom level acceleration structure. It might not be present at the moment. And at the moment, this is an operation that more or less requires some CPU work, because we have to allocate the graphics memory space for this BLAS and then record some command buffer commands to actually build it. And this means we require a round trip when we are actually activating a new instance. And this can lead to some really nasty artifacts like shadows and occlusion, or even whole instances popping in when we move around through the scene. We propose a mitigation for that problem, which is that we check, this time on the CPU again, in each frame before we are like recording the TLAS build commands, whether instances have newly appeared in the frustum. And with newly appeared, I mean that either instances have been created inside the frustum, or that the camera have moved in a way that instances that were not visible before in the frustum are now inside of it. And for all of these instances that have newly appeared, we make sure that the associated BLAS is built and also that the instance is in an active state. And this means we have, at least for the instances inside of the frustum, no latency at all, because we can ensure on the CPU side that we have all the data we need and that it is included in this frame we're currently processing on a GPU. We might activate too many instances with this. We also employ some heuristic for this, but this might still happen. But the good thing about this is that light path guided culling will then quickly deactivate these instances again because they're not receiving any light paths. And in theory, we still have the problem that when we are looking through a mirror, so instances are not inside the frustum, we still have this latency of a couple of frames. But in practice, in a real-time renderer in a game, this wasn't really noticeable at all. All right, but we have to ask ourselves, can we really cull any instances at all when we are doing path tracing, right? Because even if an object is just really small or just encountered by a small number of light paths, we can expect to get some artifacts when we just cull it and then move around with the camera, right? Once again, artifacts like objects or shadows popping in, AO popping in, stuff like that. And this culling strategy I've shown you is really interesting mainly for hybrid techniques. So what we're doing in the pipeline we're proposing for hybrid path tracing is we are rasterizing the primary hits. This is a common optimization, but it also leads to the result that instances that are culled from ray tracing, or path tracing in this case, are still visible on screen. And what we also do is that we rasterize the shadows of culled instances into a shadow map. And then during ray tracing, we combine the ray trace shadows with the shadows from the shadow map. And obviously, the shadows from the shadow map will have lower quality, but they are only in place for the instances that are deemed not important, right? And this is only so we can guarantee a visual baseline, that our renderer will never look worse and will not have any artifacts not observable in a traditional rasterizing renderer. On the other hand, this enables us to employ some pretty aggressive culling, right? We could even go as far as to say, well, we only want to have the 10 most important instances inside of our acceleration structure, and all of the rest gets culled away. And all of the rest will then just be rendered basically via rasterization, and only the most important instances will get correct ray trace lighting. And what this basically gives you, if you want it, is 80% of the visual quality for 20% of the overhead, at least concerning acceleration structures. And the cool thing about this hybrid approach is that we can utilize the GPU pretty well. So our pipeline makes use of asynchronous compute to overlap the acceleration structure building, which is a compute core heavy task, with the actual rasterization, which is more of a fixed function heavy task. And if you have a look at the evaluation, once again for the city scene in Enno that I've shown you, but with a lot of animated instances running around the scene, we can see that with our culling we can now achieve real-time path tracing in 60 FPS at 1080p, but only on the most powerful and most recent GPUs. And we can also see that on older and less powerful GPUs, we fail to achieve even 30 FPS at 1080p native resolution. But those GPUs could still fall back to some more lightweight ray tracing algorithms. If you now have a look at the different optimizations that we propose in our paper, we can see that with all of them applied, we can actually reduce the path tracing time from almost 50 milliseconds to below 20 milliseconds. And this is really the difference between real-time rendering and not real-time rendering, right? And another interesting thing we can see here is that the lowest bar in the path trace section is when we apply our culling algorithm, and we can see that path tracing gets a bit slower. This is because we have to handle the bounding boxes and increase the counters in the hit feedback buffer, but still overall we can see that the frame time is reduced significantly. This is because the acceleration structure building is so much faster. All right, and if you now look at the graphics memory consumed by acceleration structures, we see that the TLS memory consumption goes down. And this is because we significantly reduced the number of instances. But even more importantly, the graphics memory consumed by unique biases goes down. And this basically means those bottom-level acceleration structures that are associated with just a single instance. So those acceleration structures that cannot be shared between instances, for example, because some animation is running on the mesh. And this goes down from like almost 300 megabytes to below 1 megabyte, because most of the animated instances in the scene are not really that important. When you have like many hundreds or even thousands of units roaming the streets, it's probably fine to not include them, or to only include like the instances that are really close to the camera, because everything else doesn't really make that much of a difference in the final image. All right, so the conclusion of the work is pretty much that hybrid path tracing is a promising approach, and it's basically here to stay, I guess. It can work in real time, at least for scenes like the one. Sorry, folks. Okay. Yeah, so hybrid path tracing looks promising, I would say. And furthermore, what we've shown is that culling algorithms for real-time ray tracing, and especially real-time path tracing, are quite important. You can achieve significant speed-ups with that, and those are really important to achieve real-time performance. We've seen that light path feedback is really valuable. So it's not commonly used that much, as far as I know, but we think that there is a lot more potential in this that is not yet discovered. So first of all, I think we could gather more information about it. So we could, for instance, consider the ray type on the light path. And we could also consider things like ray differentials. So how important is this ray really for the lighting of the scene? And then furthermore, I think we could use this information to drive a lot more like decisions during path tracing. For instance, when an object does not get hit a lot, it doesn't really need a high level of detail, right? So this, like this decision can probably be driven by that information as well. All right, that's it, and I'm happy to take questions. I mean, okay, the question is when there are many characters roaming the street in a city, if they are all classified as less important. And it depends on the number of light paths. So if you like zoom in on one specific instance, then you can like expect many light paths to hit that instance during path tracing, right? But when you're like zoomed out and all of these instances are really far away, then usually like any single instance will only be hit by a very small amount of light paths. And therefore, yes, they will be classified as less important. Yeah. That's a good question. The question was whether I know of an example where this culling algorithm does not work at all and how this example would look like. I'm not aware of anything, to be honest. I think it all depends on the culling heuristics you choose, because at the point where you toggle the state of the instances, there's still some heuristics at play, right? For instance, in our implementation, we have some activation and deactivation thresholds, depending on the number of light paths. And if you configure these incorrectly, you might get instances where you would expect stuff to be included in ray tracing, but it actually isn't. So yeah, tuning these heuristics can be difficult. Yeah, sure.
You talked about the latency problem, how there would be pop-ins unless you use the CPU approach to figure out what was appearing. I'm curious, it seems like those things would be just outside the viewing frustum most of the time. So could you potentially increase the field of view a little bit to get the rays to catch those things before they come on screen, and just don't draw those?
Yes, I think this is a good idea. And like if you do this without the light path guided culling thing, if you just do your approach, then you will still have issues with like things you see in mirrors, right? So you need the light path information still, but including that in the mitigation is probably a good idea. Yeah. All right.
Can we thank the speaker once more?